Hello and welcome to Explaining Rust Analyzer, a video series where we try to understand how Rust Analyzer works one subsystem at a time. So, we are in the middle of looking into the parser of Rust Analyzer. Uh, last time, a couple of last times, we covered the overall philosophy of parser, the event subsystem, and the event processing code, which converts from events to syntax trees. Last time, we covered the overall parsing API and inline tests. And today I would like to just dive right into the grammar, or right into the meat of an actual parsing code and see how we parse the stuff. So without further ado, let's get started. Okay, so as a reminder, the actual grammar well, we don't have an actual grammar because we have a handwritten recursive descent parser, but the actual parsing code is in the grammar.rs file. And let me close Telegram so it doesn't interrupt us. Okay. So the grammar starts from an entry points module, which lists all the entry points, and the main entry point is the source file. The grammar contains several nested modules. Each module starts with this use super star declaration, which we use to create this like fill-in that you are writing this embedded DSL where you could just refer to any other rule in the grammar. And notice how every rule here is just a top-level function. Rather than making all these parsing functions methods on the parser like p.parse item or macro, I just make them top-level functions to get again this more like DSL fill-in, as if you are writing a BNF. So typical parsing rule looks like this. We start a syntax node. We parse the contents of syntax node by calling into the parsing rules which parse constituent parts of this node, and then we complete the syntax node with a specified kind. So here to parse a file, we first parse hashbank line, and then we parse module contents. And when we parse module contents, we repeatedly, until we reach either an end of file or a closing curly brace, parse an item or a macro invocation. So an item would be things like functions, and macro invocations are things like this path, bank, and then either round parentheses with semicolon or curly parentheses, or square parentheses with a semicolon as well. Okay, so let's look at how we parse item or macro. First of all, again, we start syntax node, and you notice that this is an item or a macro. So at this point, we do not yet know which one are we parsing, and that's why we don't specify the kinds of syntax node at the start. Then we parse outer attributes, and again, outer attributes can either be a part of an item or a part of a macro call. And that's why we kind of like can parse the common prefix of both nodes without knowing which specific node we parse. Then we try to parse an item, and by convention, functions which try to parse something but may consume no tokens start with an opt prefix, optional. So if we see an item, well, we return from this function because opt item will consume the item, and it takes this marker so that it can complete it. If we haven't seen the item, then this opt item function will return the same marker which we have passed into it, and then we will continue parsing paths, parsing macros, macro invocations. So if we didn't parse an item and we are at the start of the path, then we parse a macro call and complete a macro call. Otherwise, this is not an item, and this is not a macro call, so this is an error, and here we parse error cases. I think I will return to error recovery, error resilience somewhat later, but let's now look at like some usual parsing code. And actually, parsing attributes is a good case for this. So attributes are stuff like this. Really should have test in utter to like in an attribute would be a thing like this. And an outer attribute would be a thing like this. Okay, so this is relatively simple. And let's actually look at the outer attributes because that's what are we calling in parse source file function. So we parse actually a sequence of such things. So while the current token is a hash bank, we parse an attribute. And notice an interesting point here is that what we are doing here essentially is that we are looking at the first token. Like we check that this is a hash. And then in an attribute function, we actually assert that the first token again is hash. And then actually when we start an attribute node and then call a bump function, we again assert that this is a hash. To remind you, what bump does is it advances over one token of input, but it also makes an assertion that the token which we have consumed has the specified kind. And originally, while I was like writing the parser in one of the early iterations, I was really annoyed at this duplication. That really kind of like at this point, we already know that the current token is hash. So we probably want to actually do something like this while like if you want to like dry out the code. Like while we eat the hashband token, then let's like parse utter body or something like this. But then I realized that I'm just like worrying about really nothing, and that the parser becomes much easier to maintain and much easier to reason about if you actually have this like slight duplication. That at the start of a function you assert what should be the current state of the parser, and at the code which calls this function you kind of like also check for the state, because like actually doing this lookaheads correctly can get pretty tricky, and with these assertions you catch a lot more errors when without them. I don't think that they actually impose a significant runtime overhead. I've never actually benchmarked it, but maybe it's actually the case. But even if it is the case, then it would be relatively easy to just disable these assertions at all. So that's like the general shape of the parsing code. We check some precondition, and if precondition match, we dispatch to some parsing function. That parsing function first asserts a precondition, and then it starts the actual parsing. So we want to parse an attribute. We start a node. If this is an inner attribute, we also bump over bang, and again, this is an assertion. So it's like the precondition of a caller that probably should have been written like this, and not inner at and at 1t. Okay, so that's kind of like the true precondition of this function, but anyway, it's probably 2 euros. So after we passed like the tokens which introduce the attribute, you actually parse the thing in square brackets. So if we are at a square bracket, we eat it and like parse its internals. Otherwise, we emit an error, but we still continue parsing. So you see here how we are error resilient. So if we have something like nonsense here, okay, let me do mod scratch. By the way, like live pro tip, the way to create a new module, a new file when you write Rust is not by creating a file in Explorer. It's actually by writing mod name of the module, semicolon, and then invoking the quick fix on this module. That way you don't like need to care about which directory you need to put it and all that stuff. Okay, so let's see what we get here. Scratch. Oh, nice. This thing even tracks switches between editors. That's cool. Huh? Okay, yeah. You see that kind of like we parsed. We started to parse an attribute. We didn't see the square bracket. So we finished attribute at this point and then parsed nonsense as just like a beginning of the macro call. And that's, in a sense, what error resilience is about. Rather than like doing error and return, you just do error and then you continue parsing whatever you were parsing before. Okay. So let's now get back to the heavy math. So if we add the opening square brackets, we parse its internals, and then we expect a closing square bracket. Again, as usual, if we didn't see one, well, we emit error and carry on. And the meta is like things like derive, debug, clone, or deprecated, blah, 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 or I don't know, something like Tokyo main. Again, like you see that like this actually misses this inline test because I have to explain what a meta is instead of just like showing you the actual test. But well, test coverage always can be better. Okay, so basically we start the marker, then we parse a path, and then if the current token is an equality assigned, we bump over this equality token again. Like you see, like this is not dry code. We have like literal stupid duplication here, and like originally my hands were itching to like remove this because like why do I need to repeat twice what token I'm skipping right now? But again, then I realized that this duplication is actually great because it makes a parser so much more understandable. And yeah, then we have parse an expression, and for some reason, yeah, so we are parsing expression, and I guess it either returns doesn't, yeah, the signature doesn't make sense to me. It should be something like this, I suppose. So we either parse an expression or we fail completely. But anyway, probably like neither factor. Anyway, if we didn't parse an expression, well, we just return an error saying, hey, we kind of like expected an error, and again, we like just carry on. If the argument starts with any kind of parenthesis, the argument is actually arbitrary token tree, and that's kind of like one thing I'm like not entirely sure about. So that means that you can say like things in Rust like utter a fan main blah blah blah. So like you can put arbitrary stuff inside attributes, and I'm kind of like torn about this. It seems like restricting this to expressions would lead to kind of like more like less orthogonal but probably like easier language. But anyway, doesn't matter. Yeah, so like the parse with token tree thing, which is just basically a sequence of balanced parentheses, and that's it. And actually, yeah, I guess like what happens here is like not terribly important, but again, like we are reading a parser, so let's like just understand this. So we are parsing token tree. This is a sequence of balanced parentheses, and like some other tokens. So first, we again like this is actually an assertion because we assert that the current token is one of opening parentheses, and here we compute the closing parenthesis for current token. Then we start our actual token tree. We bump over any token, and again, this actually could have been an assertion because we know that we bump over one of those three possibilities. But anyway, like bump any, which doesn't check a specific token, is just an easier way to write that. And then until we've reached an end of file or we reached the closing parenthesis, we look at the current token. If it is one of the closing parentheses, we, well, just parse the token tree. If it is a closed curly brace, when then we've hit an match closing curly brace, and we bail out of parsing token tree without actually eating these closing parentheses. And that is kind of important. One of the invariant we try to maintain in this parser is that the sequence of curly braces is always balanced. Basically, if you look just at the tokens and you reconstruct the sequence of balanced curly braces, if you superimpose syntax tree over this balanced parenthesis sequence, then curly braces will always enclose some node in the syntax tree. And we use that for incremental parsing because if a user types anything except for curly brace, we can reparse only the node it's easier to just show. Okay, so let's say that this is parse 3, and then we typed something like boom here, and that might even be syntax error. So the parser invariant says that although this is like arbitrary like thing, as long as the change itself is a balanced sequence of parentheses, then we still parse this enclosing parentheses as the same kind of syntax node. So that means that when you do an edit, you can always find the smallest enclosing pair of corresponding parentheses and reparse just that syntax node. That is like very fun. And the fun thing here is that we don't actually use this incremental parsing like for real. So although we have this technology, when the user actually types in the file, we just parse everything from scratch because it turns out that that's fast enough. Anyway, basically, the bottom line here is that we do not, in case of an error, we do not generally want to eat a closing curly brace because that might break the sequence of balanced parentheses. If we, however, matched any other unmatched parentheses, we actually do want to skip over it. So if, for example, we have some macro invocation and it has some extremely unbalanced garbage like this, we actually still want to skip over all of this garbage and to contain it within this outer curly brace sequence. Okay, so yeah, we kind of like eating things, and in the end, we actually expect to see a closing parent kind. So we like the second stopping condition here is that we have reached the end of file. So like cases like this, where like there is like nothing after the open curly brace, and then we like emit this syntax error. But in the normal case, we actually like hit this case and it's the right token. And again, kind of like this is the expect API. So expect like tries to eat the token. If it eats the token successfully, just returns true. Otherwise, it returns false, and it also emits an error using a pretty horrifically ugly error message. Okay. One interesting thing to note here. So this is not our first loop. So we saw the loop here, like parsing token trees. We also saw a loop here and here, like when we parse attributes. And we also saw a loop in the module contents, where we kind of like parse a sequence of items. And again, while I was originally writing this parser, I was kind of like really wanted to extract this because, well, clearly we are parsing a sequence of an items. So it clearly makes sense to introduce something like sequence, which takes a parser and takes a high order function which takes parser and say returns bool and runs this parser in the loop. So essentially this is like while f of p or something like that. And I think one of the earlier versions of the parser actually contained that code, but then I realized that this high order function actually makes the code harder to read. And it doesn't help with like code correctness or code understandability at all. And the reason for that is that, well, while itself is a high order construct, in the while loop, you have a body, well, you have a condition, and you have a body of the loop. And it just kind of like, this is exactly like what this code does. It like runs the body several times so that you don't have to copy paste it. And by wrapping this into high order functions, you achieve basically nothing. You just write a worse syntax for a while loop. And again, that's kind of like an interesting insight here in that there is kinds of parser combinator libraries are pretty popular, and they allow you to write these like high order DSLs for parsers, but actually they are like 0.1 in terms of lines of code in comparison to actually just like writing the thing itself. Well, some parsing combinator libraries adds like fancy things like memoization, and that is a little bit harder to handle in this like immediate mode parsing. But for this case where we don't do any kind of memoization and where we just like straightforwardly parse everything in LL style, like the difference between handwritten parser, grammar, and parser combinator isn't like big. Like it's like a little bit different context. Like I don't know, if you write this as a grammar, it will probably be like twice as small, but it wouldn't be like logarithmically small or like square root small. So yeah, just write simple code, which is like perfectly easy to understand, and that will work for this use case. Again, as I've said on the last video, like the primary benefit of this parsing style is that it's like stupidly simple. You just look at this like sequence of straightforward function calls, and it's like crystal clear what is actually happening. Like there is nothing high order happening here. The main drawback here, though, is that you do not really know what kind of language are you parsing. Like, we are looking at this parser, and I bet that it has a couple of bugs. I'm sure that this grammar doesn't parse the Rust syntax exactly. And that is because this is like handwritten parser, which wasn't like fast against the proper grammar implementation. And that what parsing techniques based on formal grammars give you. They give you an assurance that what are you parsing actually corresponds to some grammar, and that the grammar itself is reasonable. It is like unambiguous and like some other properties. Anyway, let's continue looking at how we parse things. So I guess we've like finished parsing out attributes, and now like we completely understand how the parser will handle like things like this. So let's now look at something. So we are in the items module. Let's now look at something really interesting. How we parse an item. And like that's actually like one of the more complicated functions here. So it's like not some toy simple example. It's like a real thing, and if we understand it, then we will understand like most of the parsing here. But it is also not that hard. So what's an item? An item is like basically anything you can see at the top level in the Rust file, well, except for macro invocation. So it's like functions, struct, use items, whatnot. Items can start with visibility, as you see right here. And again, like reminder, we use pub super visibility here to work correctly with this use super : star pattern we use everywhere else in the grammar. One interesting point here is that if we look at the item or macro, it takes only the parser, and then it starts the marker, and then it passes this marker as an argument to an opt item. And yeah, important point about the marker is that it isn't clone, it isn't copy, so it's like linear type, and it actually has like this drop bomb thing, which will panic if you do not complete the marker. So this is like we at runtime try to enforce the real linearity of these markers, because marker represents an unfinished syntax node, and for every syntax node that you have started, you have to either finish it completely or you need to abandon it. You need to say, okay, so like this actually wasn't a syntax node, and let's attach the currently parsed children to its parent. Okay, so we are parsing an item. We've already parsed out attributes, so they are children of this current marker, and we need to parse the rest of the item. We start with visibility. Things like pub super. And visibility is relatively straightforward. So if a current, basically, let me fold this. Yeah, basically, there's like only 3 cases. Pub, which might be followed by like pub specification. Crate, which is an unstable syntax, or nothing. And again, this is optional, so it is correct for this code to consume 0 tokens. And if we didn't see visibility, we return just like false. Okay, so in the case of a pub, we start visibility token, we bump over pub. If we are not at the opening parenthesis, we just complete visibility and return true. Otherwise, we need to do some funny disambiguation. So, first case is that we have just pub crate self and super, and that's conflicts with things like this. So here, like you see that like this super obviously isn't like this isn't a visibility specifier. Only pub is a visibility specifier, and this is actually an item. It's kind of like genuine ambiguity in tuple structs. So here, like yeah, we check like this visibility is like one of the tokens, and it shouldn't be followed by a colon. As a reminder, the parser gives us unglued tokens, so instead of giving us a single colon token, it gives us just a colon and then a second colon, and if we want to glue them into the colon, we need to do it ourselves in the parser. So anyway, if we don't see a colon after that, then we just parse this creator super, and we parse it with a use path to like create like a real path out of it. And then we enclose this thing into parentheses. Separately, the more verbose form contains pub, in, and the actual path. Here is like, again, nothing too complicated. Bumping over, opening parentheses, bumping over in, and again, like this is actually like assertions, because we know that the first token here is opening parentheses, and the second token is actually in, because I believe what we are matching at here, what we are matching at is actually look ahead by one token forward. And again, you see that how like maintaining this context in your head is pretty hard, because like we don't actually see on the screen what we are matching on, but having these assertions in line helps us to understand the context of the code. So okay, that's how we parsed visibility. So then we actually have like a whole lot of other visibilities. We have a whole lot of other modifiers like visibility. We have const, we have async, we have unsave, we have extern, we have contextual keywords, author, and default. And like default is like particularly like I hate default because it's like so hard to parse. It has like all this like special cases. That's like existential for like existential types, and then actual items. But there is a small subset of items which actually aren't allowed to have those modifiers. And well, not small subset of items, but like a relatively interesting subset of items, and we parse them here. So that's like the list of most items we have here. And again, so extern crate. Extern crate should be easy. We bump extern, we bump crate again, asserts. I really love assertions. So we take a marker. That means that the node is already opened, and then we just bump over two known tokens. That means that the call side must actually check that the first two tokens here are extern crate, and indeed we check that the current token is extern crate, and that the look ahead, that the current token is extern, and that the look ahead is the crate. Okay, so here we have a special case. We can say extern crate self. I think this is like for a name, and extern crate self as tracing or something like that. By the way, tracing is like really cool crate. I recommend checking it out if you haven't before. So yeah, we just like parse the self. Otherwise, we expect an identifier, and to parse an identifier, we check that we are at the identifier, start the node, bump over this token, and complete the name ref syntax node. And I think I've covered this on one of the earliest lectures, but let me repeat. We have two kinds of name tokens in Rust. So like you might think that like these two foos are like actually like the same in terms of syntax. It's like just functions, but that's not exactly the case. If you look here, you see that the first foo is a name, and a second is a name, a reference. And the difference is that names are the things which introduce identifiers into the scope, while name references are, well, references to an existing names in the scope. So in the extern crate, that shouldn't. Well, yeah, okay, yeah, kind of like extern crate is kind of like a use, and that's why you parse it as a name reference. But for example, in external create foo as bar is genuinely a new name which is introduced in the scope. So that's why when you parse this rename, and again, opt means that it's optional, we parse the name as name. Well, and here is actually an interesting case. Yeah, I guess let's look now at the struct. This would be slightly more interesting. So yeah, so struct and union actually have pretty similar syntaxes. Basically, they only differ in the leading keyword. So that's why we just like eat this keyword. And in the case of union, the keyword is contextual. So we use slightly different assertion, and we use like bump remap to actually convert this contextual keyword on the lecture token layer to an actual keyword on the parser layer. Okay, and then basically we go to the meat of a parser, which parses structs and enum. And here we parse again name, but we use a name R function, and R stands for recovery. And what this does is that it gives you, well, ability to be error resilient. What you parse here is a recovery set. And this is essentially a follow set. So if you read the Dragon book, you know about like first and follow sets. So this is kind of like, you can roughly think of it as a follow set for an item, a set of tokens which follow an item. And the semantics here is that we are trying to parse a name, and we expect an identifier. But what if we store something else? What if we store something which is not an identifier? Well, then if that thing is not a recovery set, we will actually eat it and emit an error and say something like, hey, we wanted to see, well, I can just show it. So we are expecting an identifier, and let's see if we like saw something else. Then you see that this error actually encloses this erroneous token. And then we continue like parsing the struct as usual. However, if the thing here is in the recovery set, we don't parse over it. And what would be a recovery set here? Well, a common case would be a function, because imagine that you have like this code, and then you start typing. So, let's actually add more white space here. Yeah, you start typing, and it's okay. Can I just disable autocompletion pop-up? Okay, I can make it more narrow. Okay, perfect. So I'm start to type here, and I don't want this function node to disappear from the syntax tree. So when I type the struct and I'm expecting identifier, I want to see an error, but hey, a name is expected here, but I don't want this name to actually eat over the FN token. And that's exactly what is happening. So let's actually look here. We invoke name error and we parse item recovery set. Item recovery set contains a fan token. So here, if we are not eating an ident, we call error and recover. And again, at first, we special case curly braces because we do not ever want to eat over a curly brace because we need to keep those balanced. And this thing is for macros, and I don't think it works correctly, and I actually want to fix it one day, so yeah, just ignore it, pretend it's not there. Then if we are at a token set, at a token in a recovery set, then we just emit an error message. Otherwise, we actually start an error node and we bump over the token from outside recovery set, and then we emit an error message. That's kind of like one of the small tricks how you make parsing resilient. And again, no matter whether we parsed the name correctly or not, we just continue parsing of the code as if nothing happens. And that's the beauty of this error recovery approach. You see that there is literally no place where we explicitly handle errors, explicitly try to recover from errors. We just write straightforward code to parse Rust. The only thing we do is that we do not fail on error. We just continue as usual. And that's mostly it. That's mostly everything you need for error recovery. So, okay, let's actually look at how do we parse structure or a union. First of all, we start parsing generic parameters, and yeah, I guess generic parameters is something I also want to cover in this lecture, and probably we will then stop at generic parameters. After we parse generics, we can parse a where clause, and yeah, that's actually this badly misses inline test, because it would really be useful to understand how can we get to the state we have this where clause and just semicolon after that. I think it's something like struct as tt. Actually, can I write this like this as self copy? I have no idea if this actually compiles. Okay, let's comment this out. It's overflow evaluating the requirements as column copy. Yeah, that's nice. I think it could have been a better error, but apparently you're actually allowed to write code like this anyway. That is why inline tests are magical, and that's why we need more of those. So we parse where clause. After where clause, we basically have three cases. Either we have a record struct with curly braces list of fields, or we have a unit struct in that case we have a semicolon, or we have a tuple struct, and in that case we have this round brace. Okay, so let's look at the record field list again. As usual, we dispatch the current token. It is opening curly brace. In the record field list, we assert that the precondition holds, and then we start parsing. So we bump over opening curly brace. Actually, this should be flipped, because it's we always start with checking for e off. And again, it's kind of redundant. In every while you have to check for end of file, because well, that's a possible stopping condition for you, and it feels really bad that you need to repeat it. But it's not actually that much code, and it's very easy to understand, and extracting it into some helper function would actually make the code harder to understand. It's just write this if not at e off. What does help here though is having actually non-verbose names for things you constantly use. You see that the parser is always named P, and this is very intentional. It's not because I hate long names. I love long names. Without a completion, I like to just put all the words there is in a single name, because that's make the code more readable. But actually, you see, it's the name of the function is pretty verbose. Record field list, it's exactly spells what it is parsing. But this P is used throughout the code. It is very frequent identifier, and that's why it makes sense to use a short name for it. Similarly, start, bump, and especially at are very short names, and they are intentionally short. Okay, as usual, so we parse a colon-separated list. This is a list inside a curly brace, so we need to maintain balanced curly braces, and if we see an unexpected curly brace, when we actually have to eat until the finishing curly brace. Inside this loop, we parse a record field, and this is like a cute idiom for parsing a comma-separated list with an optional trailing semicolon. So the condition here is that actually let me show you this in generic parameter because right, yeah. So yeah, let's actually compare like these two loops. So here we parse a comma-separated list of fields in a struct. So like this thing. And here we parse a comma-separated list oh, interesting. You see how it shakes while I'm typing? I wonder why is that. Wow, it's I like this effect. Sorry, I'm a stupid 5-year-old. Okay, so this parse a comma-separated list inside curly braces, and this parse a comma-separated list inside angle brackets. And that's actually like the condition which I wanted to show you originally. Like that's kind of like the canonical parsing of a semicolon separated list. Until you are at the end of a file or you are at the closing parenthesis, you parse whatever is the body of the thing, and then you either you either expect a comma in the next item, a comma and a closing parenthesis, or a closing parenthesis. And this code does exactly like this. So if you parsed an item and then you hit a closing parenthesis, then you hit this break and without hitting parenthesis, and you eat parenthesis afterwards. If you parse an item and you see comma, then you fall through this condition. You eat the comma here, because if you're not in the closing position, then you are expecting a comma, and you actually should emit an error if there isn't one. Anyway, so you eat the comma, and then you get to the next iteration of the loop, and you break through this condition, and then it the closing thing. Otherwise, if it's kind of like neither this thing, neither that thing, well, you just break out of the loop here because, well, that's an error, and you shouldn't be parsing it. There is a slight modification here, is that if you're also kind of like not at generic param first, again, like this is like first set. So if you are seeing something which isn't a comma, which isn't a closing parenthesis, but a thing which actually can start a new generic parenthesis, you can just emit a missing colon error and continue like to the next iteration of the loop to recover from missing comma. Because I think so. Let's actually I wonder if we should just like write this. So you see, like we parse this correctly, but if we parse like x, y, z, then like the whole thing is highlighted in red. So we don't properly recover from missing semicolon. And I think let's actually just fix it. Like I don't promise you that this will be a correct fix. a correct. Do we actually have first sets here? Yeah, so we do have correct first sets here. So yeah, let's actually do just like a bit of live coding to show this. Basically, what we want is we want to have a test for recovery. So this needs to be an error test. And error means that, hey, we are expecting an error here. Recovery after colon. No, I hate this name. Colon. It's comma. I always forget like how many M's are there in a comma. Anyway, drink parameter list comma recovery. Okay, so X, Y, Z. And let's write syntax. And let's test it. Okay, so I think we... Okay. We also need update to pass update expect, and now we have this file. So it's copy-pasted from the actual source code, and it contains the IST. And here in IST, you see that we like recognize X, Y, and then like we think that Z is actually like a macro call, and then everything goes downhill. So that's like not what we want to see here. We actually want to recover. So let's define const generic param first. Token set. Is it like new? Okay, and here we need to parse the syntax kind, and let's just like look at the generic parameter. What would be the first set? So outer attribute, so something like this. And again, kind of like first set. If you have a grammar, you can actually like compute first set automatically. And in this approach, you need to do this manually. And if you mess up like that, might mess up your parser. And that's definitely like, well, some extra work you accept if you choose to write a parser by hand. So again, I really love this parsing technique, but I really wish that I don't have to use it and that I just can use an automated parser generator, which like does the right thing for me. It's just that no one has written such a great parser generator yet. Okay, so lifetime ident const, and I think it's it. Actually, like we really should be doing that. Okay, and not again. You see, like this is exactly the case. Well, like this same kind of error recovery is, well, I guess like not the same kind of error recovery because it's not released, but kind of like similar case of error recovery, because like we it seems like the syntax tree is like completely broken here and we get to the break, but we've just like missed the binary operator, so like we should be smarter here. At TS. Okay, so this should be better. Now let's update our test. Oops. Sorry, I have deleted the actual test here. Okay, and now let's just retype everything again. Yours. Okay, let's look at the IST. Okay, yeah. Much more visible now. So we have like x, y, and z as the type parameters, and then we have like correct sequence of parentheses, and then we have expected comma. That's actually just courageously rebuilt, or like why I'm rebuilding everything from scratch. Okay, let's just courageously rebuild everything from scratch and see that this actually works in our live editor. It might have broken something else, I'm not sure. We'll see. Okay, and while we're at it, let's go back the stack. So we are looking at what we were doing even. Oh, right. We were comparing how are we parsing comma separated list in generic parameters and in record fields. And the difference here is that here, like we actually have this constraint that we keep curly braces balanced. So we don't have a break in this if. So if we saw like we wanted to see either closing curly brace or a comma, and we see neither. So it's clear that something's wrong with our record field list, and we ideally should like just bail out of it, but we don't do, and we like continue parsing to make sure that we correctly eat the closing parentheses. Here we just break out, except for the case where, well, we actually have this generic parameter. Okay, and let's now like look at what we've done. So again, the case is like this. We have like x, y, z colon. And if we forget the semicolon, like the syntax tree is like fully a mess. We type param. Hmm. Wow. How is this happening? Like it seems like I don't understand this. Yeah, anyway, yeah. So yeah, probably. Yeah. So yeah, basically, yeah, it's interesting. Like you saw that, like basically, while we parsing the module context, is either a macro, it's either an item or a macro call, and the macro call starts with a path. So you see that like when something goes seriously wrong, we just like parse everything as like macro calls. So you see kind of like the tree is a mess. And now let's like reload the thing. And you see now it's like much more reasonable. We have only a single error that like we are missing a comma here, and we fully recovered the rest of the syntax tree, which is great. Okay, I feel like this probably is it. I wonder if like there's anything else specific I wanted to discuss here. Yeah, yeah. I don't think there's actually anything else to parse in. You just like parse like the sequence of like comma separated lists, and then yeah, like the actual field, well, by this time you should probably guess how it looks like. We parse out attributes, and when we parse optional visibility, and then if we are at identifier, we parse a name, and then we parse type, and that is a record field. Otherwise, oh well, that's like a button is probably interesting. We should explain this. So we are parsing a field because we know that like the only thing which can happen in this position is a record field. But if we didn't parse even an identifier, we actually, yeah, I wonder. Yeah, it's probably not really important. Yeah, I guess my thinking here was that I don't want to emit record fields which do not have identifiers, but that probably would be fine. But anyway, just to show this specific case, yes, let's open our Scratch buffer. So if you have something like pop92, you see that we don't like we emit visibility token, but we don't actually emit a field token here because yeah, for some reason I thought that fields without names are like bad thing to have in a syntax tree. Actually, oh well, that might be a reason for that. For this, let's look at the generated IST. So what we are looking at, okay, yeah, and like the generated IST we'll probably be covering in the next lecture. So let's look at the record field, and it is name owner, and like the name is still optional. Yeah, so like this, yeah, this. I wanted to explain like why we need a button here, but we don't actually need it. We could get by without abandoning this and just emitting like a completely incomplete record field. Okay. So I hope that like gives you a feeling for what parsing in this IDE-friendly, error-resilient sense is, and it's like really not different. Well, it's different. It's not complicated. So let me sum up main points. First of all, yeah, let's sum up like the main points of like this style of writing parsers. First of all, you are writing a lossless parser. The goal of a parser is produce the syntax tree even from completely invalid syntax code, and it should produce as much syntax tree as possible. You want the parser to be simple, so you just going to write it by hand rather than using some complicated parser generated machinery. And you're not necessarily want, but you are willing to pay for it with correctness, because making sure that this style of parsing is actually correct is very hard. Well, I don't think it's like very hard. I guess like with proper testing, you can actually ensure that this thing parses the stuff correctly. But again, it's kind of you don't get it for free like in parser generators. Yeah, and you also kind of like want the parser to have like this simple and understandable feeling of just like using functions. How you do it? First of all, you separate parsing API from the grammar itself. You have a parser struct which contains a source of tokens and a bunch of methods for inspecting the current token, doing lookaheads, and producing a syntax tree. And the parser doesn't have any methods for actually parsing the actual productions of your language. For productions, you have a separate grammar module which contains a tree of submodules where each module is just a bunch of functions. All these functions take a parser, immutable reference to a parser, as the first argument. They are named after productions in the grammar, and they just parse the things. Every such function, like, I don't know, lifetime arc. Well, let's Yeah, let's actually look at the records list, for example. Every such production starts with asserting that the current token is what is expected. Although you could optimize this and you could eat the first token at the call site, I would advise against doing that. I would advise that the call site just does a look ahead, and then the Kali basically redoes this look ahead and emits an assertion, a panic, if something goes wrong. Because if something goes wrong here, that means like your grammar is wrong. Because again, it's very hard to write this thing correctly, so you want as much help as you can from your assertions. Yeah, and then in like this parsing functions, well, you just write straightforward code to, well, parse stuff. Basically, if you have some grammar rule, you just spell this grammar rule by invoking functions. Except that, like, you don't need to deal with stuff like left recursion and lists. Like lists and lists repetitions and left recursion are very they're very hard to deal in pure context-free grammars. They are like somewhat easier to deal in parser generators, which have syntax sugar for them. But if you actually write, well, actual Rust code to parse stuff, you can just write while loops to parse lists. And you just write while loops and if conditions. You do not extract any kind of high order functions. You might want to extract helper functions, like for example, when we parsed a data type, like structure union, they both delegated to like this same function, but again, it's kind of like your ordinary boring function. It's like not a high order function. You could write that at C basically. To be error resilient, the first trick you do is that, well, you do like literally nothing. You just parse the stuff as if errors do not exist. And that gives you like halfway there. The second thing you do is that you use recovery sets. So when you want to parse a specific token, like an identifier, and a token that you see at the current position isn't actually it, it is some different token, you check if this token belongs to the follow set of the thing which you are currently parsing. And if it is indeed in a follow set, that probably means that the user is midway typing the thing. So like user typed prefix of the thing, and they are going to type like the rest of the thing very soon. But what follows after this incomplete snippet of code is actually completely valid subsequent code. So, and like what follows, again, like use follow set for that. And if it's like a follow set, you don't eat the token. If the token is like completely unexpected, well, it's fine to eat over the token and emit an error there. The second thing is that you are careful okay, that was generic parameters. You are careful when you parse the lists, basically, and that's kind of like, yeah, actually, like, this while loops is like the main focus of error recovery, because, well, you're parsing a sequence of things, and at every point you need to make a decision. Are you going to parse the next thing, or do you think that the current list has ended and what follows is actually some completely unrelated construct? And for that, you can use first sets, actually. Let's look at some other usages of first sets. Around first. What is it? Okay, that's like a list of function parameters. And again, that's like slightly more complicated while loop for parsing comma separated lists, but again, you kind of like, you see the same shape where we check at the e of and closing parentheses at the condition, and then at the end you check for like closing parentheses and a comma. Yeah, but like you also probably want to break early if this is not a valid parameter. I wonder. Oh yeah, right. That's actually probably a better way to write this. So what we have in generic parameters, is this, and what we have here is this, and that's like I like this formulation better because we don't try to parse generic parameter if we are not in the first set. So I guess we should say something like this: if then expected generic parameter, and then we just break. Otherwise, we generic parameter. No, it's yeah. Okay, so this goes away, and we replace this break with this thing. Okay, yeah. Something's broken. Okay. Why? Okay, yeah. So I was wondering why it's like shows the syntax error here and not here. Wow, because like this is a binary expression where like the left side is a bool and the right side is a block. So yeah, it's kind of like hard to understand that this is actually the place where error happens. Param pam pam. Param pam pam. Yeah. While loops are a focus of error recovery, and you kind of like make like not like really like intelligent decisions, but just like not stupid decisions about whether you should try to resiliently parse the next thing or where like the list has ended, and that's basically it. I think. Yeah, I don't think that's like anything else I want to discuss in terms of parsing for IDEs. So thank you for listening, and see you next time when we will be discussing either code generation for our syntax trees, or maybe we will look at the parsing of expressions, because parsing of expressions is actually slightly more involved than what I have been showing you before, because it makes use of parsing. Anyway, let's wait for next video to figure out. Goodbye.